Few processes in the human mind are as essential and as mysterious as memory. It is through memory that we form a sense of identity, learn from the past, adapt to new challenges, and construct the continuity of our inner world. Whether we are recalling the face of a loved one, solving a mathematical problem, or navigating a city street, memory is the silent architect of our consciousness. Understanding how memory works, from the first moment of sensory input to the intricate mechanisms of long-term storage, is therefore not only a central question of cognitive psychology, but also a gateway to enhancing learning, treating psychological disorders, and appreciating the plasticity and fragility of the human brain. The journey of memory begins with perception. As we encounter the world through our senses, an overwhelming amount of information floods our nervous system. This raw data must be briefly registered in what is known as the sensory memory. Sensory memory is modality-specific and extremely short-lived, typically lasting from milliseconds to a few seconds. Iconic memory, visual, echoic memory, auditory, and haptic memory, tactile, serve as buffers that allow the brain to hold on to stimuli long enough for selective attention to act. Only a fraction of these stimuli, depending on our focus, emotional state, and relevance of the stimulus, are filtered into the next stage, working memory. Working memory, formerly known as short-term memory, is the cognitive system responsible for the temporary maintenance and manipulation of information. It is both a workspace and a bottleneck. Baddeley and Hitch, 1974, proposed a highly influential multi-component model of working memory that includes the central executive, the phonological loop, the visuospatial sketchpad, and later the episodic buffer. Baddeley, 2000. The phonological loop handles verbal and auditory information. The visuospatial sketchpad manages visual and spatial data, and the episodic buffer integrates information across domains and links it to long-term memory. The central executive, as the name suggests, orchestrates attention, allocates cognitive resources, and manages interference. The capacity of working memory is sharply limited. George Miller, 1956, famously proposed the magical number 7 plus or minus 2, though more recent research suggests that the capacity may be closer to 4 items when rehearsal and chunking are controlled for. Cowan, 2001. Because of its limitations, working memory acts as a cognitive gateway. Only information that is actively processed, rehearsed, and encoded will have a chance of being transferred into long-term memory. This encoding process is profoundly influenced by the depth of processing, as proposed by Craik and Lockhart, 1972. According to their levels of processing framework, the more meaningfully and elaborately we process information by associating it with prior knowledge, making it personally relevant, or generating mental images, the more likely it is to be retained. Once encoded, information moves into long-term memory, a vast and complex system capable of storing an essentially unlimited amount of information over an indefinite time span. Long-term memory is commonly divided into 2 major types: explicit or declarative memory and implicit or non-declarative memory. Explicit memory refers to conscious recollection of facts and events and includes episodic memory, memory for specific experiences, and semantic memory, general world knowledge. Implicit memory, by contrast, operates without conscious awareness and includes procedural memory, skills and habits, priming, and classical conditioning effects. These distinctions were famously highlighted in studies of patients with amnesia, particularly the case of Henry Molaison, known as HM, whose hippocampus was surgically removed, leading to profound impairments in forming new declarative memories while leaving procedural learning intact. Scoville and Milner, 1957. The process of consolidation is critical for stabilizing long-term memories. Initially fragile, memories are thought to become more stable over time through a process that involves structural changes in the brain, particularly in the hippocampus and neocortex. The standard model of consolidation suggests that the hippocampus temporarily binds the distributed features of an experience, and over time, These connections are gradually transferred to cortical networks for permanent storage. Squire and Alvarez, 1995. However, the process is not linear or fixed. Research into reconsolidation shows that each time a memory is retrieved, it becomes labile and must be reconsolidated, offering a potential window for updating or even disrupting it. Nader et al., 2000. This finding has significant implications for therapeutic interventions, especially in treating trauma-related disorders such as PTSD. Real-life examples illuminate how these mechanisms function. A student preparing for an exam might use elaborative rehearsal to encode material into long-term memory, linking new concepts to familiar knowledge. When recalling the material during the exam, retrieval cues in the environment or internal state can either facilitate or hinder access. If the student has studied in multiple contexts, a strategy known as context variability, the chances of successful retrieval are enhanced. Conversely, stress or fatigue can impair working memory function and retrieval efficiency, even if the information has been adequately encoded. Memory is also highly reconstructive. Contrary to the popular metaphor of memory as a recording device, decades of research demonstrate that remembering is an active, inferential process. Bartlett, 1932, showed how people's recollections of stories are shaped by schemas, mental frameworks that influence how information is interpreted and recalled. Similarly, the misinformation effect, demonstrated by Loftus and Palmer, 1974, illustrates how post-event information can distort eyewitness memory. These phenomena underscore the fallibility of memory and raise important questions in legal, clinical, and educational domains. Reflecting on these insights, several questions emerge. How can we design educational environments that optimize encoding, consolidation, and retrieval? How might understanding the limits of working memory help us reduce cognitive overload in the digital age? What are the ethical implications of using technologies to enhance or manipulate memory? How do cultural narratives shape what we remember and forget? Neuroscience continues to shed light on the biological underpinnings of memory. Long-term potentiation, LTP, a process by which synaptic connections are strengthened through repeated activation, is widely considered a cellular mechanism for learning and memory. It is particularly evident in the hippocampus, which plays a central role in forming new episodic memories. Moreover, neuroimaging studies reveal that different types of memory rely on distinct brain networks. The prefrontal cortex supports working memory and executive function. The medial temporal lobe underlies declarative memory. The cerebellum and basal ganglia are implicated in procedural memory, and the amygdala modulates emotional memory. Sleep also plays an essential role in memory consolidation. During slow-wave sleep, hippocampus-dependent memories are replayed and integrated into cortical networks, while REM sleep may contribute to the abstraction and emotional processing of memories. Diekelman and Born, 2010. This finding has practical implications. Students who sacrifice sleep for study may inadvertently undermine the very consolidation processes they rely on to retain information. In conclusion, memory is not a single process, but a dynamic system encompassing multiple stages and mechanisms. From the fleeting impression of a sensory input to the enduring legacy of a personal memory, each step, attention, encoding, consolidation, retrieval, is shaped by cognitive, emotional, neural, and contextual factors. The study of memory reveals both the astonishing power and the inherent fallibility of the human mind. Rather than viewing memory as a passive archive, we must understand it as a living system, malleable, reconstructive, and deeply embedded in our biological and social nature. By harnessing this knowledge, we can foster deeper learning, design more effective interventions, and perhaps even reclaim forgotten parts of ourselves.